the same thing couldn't be said for Newton's law of gravity. Newton's law of gravity had to be modified with the advent of special relativity. All right, so that's where Einstein came in. So the question is then, how do you figure out how to modify Newton's laws to take this into consideration? What kinds of principles can you use? So I should say in this regard, Einstein is a very bad example of a scientist. He really sort of used leaps of logic and leaps of intuition rather than sort of incrementally deriving a new result from what was known at the time. So we're gonna follow Einstein's way of intuitively thinking about how to extend this laws. So one of the things that impressed Einstein about gravity was its universality. All right, so this is the second time that I'm going to use math tonight, and it's going to be the last time. So what do we mean by its universality? All right, so to talk about this, I'm going to remind you of Newton's second law. So this is a non-gravitational law. This is the law that relates the force on an object to its acceleration. So this is the famous F equals ma. So this is telling us that if I apply a certain force F to an object, that object is going to accelerate by an amount a, and that proportionality constant is given by the mass of the object m, like so. That's what this is telling us. All right, so again, we're going to apply this to two separate situations. We're going to apply this to the case of electric charge, and then we're going to apply this to the case of a gravitational mass. All right, so let's do electric charge first. All right, so let's imagine now that we have some little electric charge. We're going to give it a charge E, and we're going to place it in some electric field, which I'm going to refer to as capital E. All right, so the force on this charge due to the electric field is going to be proportional to the electric field itself, and the proportionality constant is simply the electric charge little e. So in other words, F is equal to little e times big E. So this is the force due to the electric field on this charge. All right, if we now also use Newton's second law, this tells us that the acceleration then is related to the force by F equals to ma. So if we solve for the acceleration in this case, we divide both sides by m, we find that the acceleration is given by the electric charge divided by the mass times the electric field E, like so. All right, so for a charge in an electric field, the greater the electric charge, the greater the acceleration. The greater the mass, though, the smaller the acceleration, right? All right, but now we can do the exact same thing with gravity. Let's use a different color. So now, instead of putting a point charge in an electric field, I'm going to put a point mass in a gravitational field instead. So I'm going to have a little object that has some mass m, and I'm going to put it in a gravitational field, say that points downward. We can think of this as being like the Earth's gravitational field near the surface of the Earth. So this is going to be a point mass in some gravitational field g, like so. And now we can do the same exercise. So the force on this point mass due to the gravitational field is going to be proportional to the gravitational field itself, and that proportionality constant is given by the mass of the point object. So the force due to the gravitational field is equal to m times g. So now again, I can use Newton's second law to find the acceleration. So this should just be equal to m times a. And now if I want to find the acceleration, I'm going to divide both sides by m, and the magic that happens here is that the m drops out of both sides of the equation, right? So this is in stark contrast to what's going on with the electric charge, where you have a charge that represents how strongly this object reacts to an electric field that's different than the mass of the object, and together these two things tell you how this particle is going to respond to an electric field. In the case of gravity, it's m that appears on both sides of the equation. So m is telling you how strongly this object reacts to a gravitational field, but it's also telling you its resistance to acceleration, so that when you actually calculate the acceleration of this object, you find that it's completely independent of the mass of the object itself. So this is telling you that every object, every mass, is going to accelerate the same way in a given gravitational field. All right, so this is what we mean by the universality of gravity. And in fact, this is the thing that lore has that Galileo was testing when he dropped objects off the Leaning Tower of Pisa. So he dropped big objects, and he dropped small objects, and he showed that they all, according to legend, accelerated at the same rate, like so. All right, so this fact really impressed Einstein, and it led him to what he refers to as his happiest thought.